Good morning, dear students. Today we are going to solve May-June 2013 2-1 paper. It's a theory paper. We call it paper 2. The course we are studying is Physics 5054. My name is Ferhan Mazher. Let's start today's paper. Okay. In figure 1.1, figure 1.1 shows how the length of a spring varies as the force applied to it increases. So here we go. So here you can see we have a length, and the length of the spring is on the x-axis and the force applied is on the y-axis. So when the force is 0, the length is 11. I hope you can see that. When the force is 0, the length is 11. It means that the unstretched length is 11. And you can see this length and force graph. It's a straight line. Determine the length of the unstretched spring. Unstretched spring, when there is no load, what is the length? So when there is 0 load, the length is 11. Simple. So here you write 11 centimeter. The next question is B part. Explain how the graph shows that the limit of proportionality is not reached. You can see that the graph, this force and length graph, it's a straight line. It's not a curve. So because it's a straight line graph, the gradient is constant throughout. It's that shows that the limit of proportionality has not crossed. When the graph is made beyond the limit of proportionality, the graph becomes a curve. The graph is a straight line, so that shows that the limit of proportionality has not been crossed. I have written this answer. Let me show you. Question number 1A part, 11 centimeter. Question number 1B part. Graph is a straight line. This shows that limit of proportionality is not crossed. Okay. C part is on your screen. The spring is attached to a mass M of 0.20 kg and placed on a frictionless surface as shown in the figure 1.2. So here we have a mass M. This surface is frictionless. It's a horizontal surface, and we have attached this mass with a spring, and this spring is fixed on this side. This side of the spring will be movable. The apparatus is used on the floor of a car. When the car accelerates uniformly in the direction shown, the spring extends. So this is on the floor of a car, but the car is moving to the right side. So when the car will be moving to the right side, due to the inertia of this mass M, this spring will stretch. State what is meant by a uniform acceleration. State what is meant by uniform acceleration. It's a 2-mark question. Uniform acceleration means that if a body is moving and it's moving in such a way that there is an equal increase in the velocity in equal intervals of time. Equal change in velocity in equal intervals of time. We call it uniform acceleration. We say that the body is moving with the uniform acceleration. So 2-mark question. I've written this answer also. Let me show you. Yeah. Equal change in velocity in equal intervals of time. This is called uniform acceleration. Okay. Second part, the extension of the spring is 9 centimeter. Using the figure 1.1, determine the horizontal force on M. Okay. So we have to use the figure 1.1. Let's open that figure. and the extension in the spring is 9 centimeter. Okay, so this is that graph. Unstretched length is 11, extension is 9. So 11 plus 9, it will give you 20 centimeter length. Unstretched length is 11. The extension is 9. So the total, the new length will be extension plus the L0. It will be 9 plus 11. So the new length will be 20. On the, here's the 20. From here, go to the graph and check what is the value of the force. What is the value of the force here? Okay. So it is 0.8 Newton. It is 0.8 Newton. So I have read it from the, I have checked it from the figure 1.1. I hope you have understood. So the answer here will be 0.8 Newton. The second part is the acceleration of M. We know the force and we know the mass of the body. So we can find the acceleration. F is equals to ma according to the Newton's second law of motion. F equals to ma. A is equals to F divided by M. So 0.8 Newton divided by 0.20 kg. And the final answer will be 4 meter per second square. I have done this on a paper also. Let me show you my work. So you can see second part, first portion. L0 is 11 centimeter, extension is 9 centimeter. So the new length will be L0 plus the extension. L will be equal to 11 plus 9 and L will be 20 centimeter. By using the figure 1.1, at the length of 20 centimeter, the force is 0.8 Newton. Sorry. Okay, F is equals to ma, A is equals to F divided by M equals to 0.8 divided by 0.20. And the answer is 4 meter per second square. I hope that you have understood it. So that was question number 1. Let's move to the next question. Here we go. Figure 2.1 shows apparatus used to investigate the turning effect of a force. So here we have a uniform meter rule. It is pivoted at the center. And here a weight of 4 Newton is hung. And the distance from the pivot is 40 centimeter. Here we have a Newton meter. So it will provide an upward force. And the distance from the pivot is 20 centimeter. This is trying to produce a anti-clockwise moment, and the force here is trying to produce a clockwise moment. Because the thing is in balance, the anti-clockwise moment and the clockwise moment, they will be equal to each other. The uniform meter rule is freely pivoted at its center. The Newton meter is 20 centimeter from the pivot, and a 4 Newton weight is 40 centimeter from the pivot. The meter rule is in equilibrium. State the principle of moments for a body in equilibrium. The principle of moments for a body in equilibrium: if a body is in equilibrium, the sum of the clockwise moments and the sum of the anti-clockwise moments will be 0. The net moment should be 0. Or sometimes we say for a body in equilibrium, the sum of the clockwise moments is equals to the sum of anti-clockwise moment. Or sometimes we say that for a body in equilibrium, the sum of clockwise and anti-clockwise moments should be 0. Means net moment should be 0. I have written this answer. Let me show you my answer. Question number 2 is on your screen. For a body in equilibrium, clockwise moment and anti-clockwise moment about a pivot are equal to each other. Okay. Then he says calculate the reading on the Newton meter. It's a 2-mark numerical. Let me go take you back to the. So here is the force exerted. It's trying to produce on the Newton by the Newton meter, and this force is trying to produce a clockwise moment. This 4 Newton force weight is trying to produce an anti-clockwise moment because the thing is in balance. So the clockwise moment and the anti-clockwise moment, they will be equal. So F multiplied 20 equals to 4 multiplied 40. So F will be equals to 4 into 40 divided by 20, and F will be 8 Newton. So the reading on the Newton meter will be 8 Newton. Let me show you my work. Okay. So B part is on your screen. Clockwise moment equals to anti-clockwise moment. F multiplied 20 equals to 4 into 40. So F will be 8 Newton. So I hope that you have understood this numerical. The weight of the meter rule is 1.2 Newton. Calculate the size of the force exerted on the meter rule by the pivot. Okay. You know, the thing is in balance. So upward force and the downward force, they are equal to each other. So, and we can find, okay, for example, I suppose that this is downward force 4 Newton. This is upward force which is 0.8 Newton. Which is 8 Newton only. And suppose here the pivot is also applying a force in upward direction. So these two forces are in upward direction and this force is in downward direction. So their sum will be equals to the 4 Newton force. So, and another extra weight they have hung here. Let me read the question again. Just got distracted. The weight of the meter rule is 1.2 Newton. Yeah. So here downward we have 4 Newton, and here the weight of the meter rule is acting at the center of gravity, that is 1.2 Newton. So in downward direction there are two forces. Suppose there are two forces, 4 Newton and 1.2 Newton. And in the upward direction here we have 8 Newton force, and suppose the force here is also in the upward direction, and we want to find out this force, and we also want to confirm that what is this direction. Okay, so the sum of the upward forces and sum of the downward forces will be equals to each other. So this 8 Newton upward plus this force F, I have supposed is in upward direction, will be equals to 4 plus 1.2. I've done this on a paper. Let me show you that work. On your screen you can see 4 plus 1.2, they are downward, and F plus 8, they are in upward direction. So the value of F will be minus 8 plus 5.2, and the answer will be minus 2.8. So the magnitude of that force will be 2.8 Newton, but with our answer we have a negative sign, and that negative sign shows that the direction which I suppose that F is in the upward direction, but the answer of the F came out to be minus 2.8. That negative shows that the direction which I supposed, the real direction is opposite to that. So the real direction of the F will be in the downward direction. So F will be 2.8 Newton and it will be in the downward direction. A little bit tricky question. So I hope you have understood it. Okay, let's move to the next question. Okay, here we go. Question number 3 is on your screen. It says figure 3.1 shows a glass tube dipped into mercury. A vacuum pump is connected to the top of the tube and switched on. The mercury rises up the tube and stops. So here we have vacuum. So the mercury was rising in this tube and it has stopped here. So I have taken a point P here, point Q here, point R here. The level of the mercury in the tray and the level of the mercury in the glass tube. The height is 0.76 meter. Three points on the figure 3.1 are labeled P, Q, and R. State which two of these points are at atmospheric pressure. So this point R is directly under the atmospheric pressure. So the pressure at point R is atmospheric pressure. This point Q, above it, this column of mercury, the pressure of this column of mercury is equal to atmospheric pressure. So at point Q and at point R, the pressure is equal to the atmospheric pressure. Okay. Above this point Q, this length, the length of this mercury column, that is the pressure produced by this column of the mercury is equal to the atmospheric pressure. So this Q is at the pressure on that Q point is equal to the atmospheric pressure, and R is directly under the atmospheric pressures. So Q and R are those 2 points which are under 1 atmospheric pressure. Okay, B part. The density of the mercury is 13600 kg per meter cube, and the gravitational field strength G is 10 Newton per kg. Calculate the pressure due to the column of mercury of length 0.76 meter. So the pressure of a liquid you can find by the formula. Pressure is equal to rho GH, where rho is the density, G is the gravitational field strength, and H is the length of the or depth of the liquid above that point. So you can put the values 13,600 multiply 10 multiply 0.76, and the answer will be 103360, and the final answer can be written in the standard form as 1 expo 5 Newton per meter square. Let me show you my work. So on your screen you can see the B part. Pressure is equal to rho GH. We put the values, we did the calculation, and the final answer is 1 expo 5 Newton per meter square. I hope that this numerical is clear. State and explain what happens if the mercury in the apparatus shown in figure 3.1 is replaced by the water. So if you put water there in the place of mercury, so if the water has to show the same pressure with the length of the water, column of the water in the same tube, because the water has less density than the mercury. The density of the mercury is 13,600 kg per meter cube. But the density of the water is 1,000 kg per meter cube. You see, the density of the water is smaller than the density of the mercury. To show the same pressure, the length of the water column will have to be larger. So the chances are, because the water has less density, to show the same pressure, the depth of the column of the water will be larger than the length of the mercury. So the length of the mercury water column will be larger. I have written this answer also. Let me show you. Water has less density than mercury. So to give same pressure value of water, the same pressure value, water column in the glass tube will be higher. Water has less density than mercury. So to give same pressure, value of the water column in glass tube will be higher. I hope that you have understood it. So that was question number 3. Let's move to the next question. Question number 4 is on your screen. Figure 4.1 shows a laboratory thermometer. State the range of the thermometer shown in the figure 4.1. The range means the maximum temperature it can measure and the minimum temperature it can measure. You check both these values and you find the difference between them. Maximum value minus the minimum value. So 110 minus 10. So it will be 110 plus 10 and the final answer will be 120 degrees centigrade. So the range is from minus 10 to 110, or you can also say if the range is 120 degrees centigrade. Okay. Describe how the figure 4.1 shows that the thermometer has a linear scale. You know, the distance between each readings is even. It's uniform throughout. So that shows that the scale is linear of the thermometer. I have written this answer. Let me show you my answer. Same distance for same rise in temperature along the scale of thermometer. So that shows that it has a linear scale. Same distance for same rise in temperature along the scale of thermometer. This is the question of the range. You can see that how we do it. Okay. Third part. The manufacturer of the thermometer changes the design to make a more sensitive thermometer. Figure 4.2 shows part of the scale on the original thermometer. On figure 4.3, draw a more sensitive scale. Okay, so this is the original thermometer. So here is 10, here is 20, 30, 40, 50, 60, 70. So in the same length, they have shown 10, 20, 30, 40, 50, 60, 70, something like 75 reading. 10, 20, 30, 40, 50, 60, 70, 75. So when you will make here a more sensitive thermometer, in the same length of the thermometer, the range should be less than 75. For example, if I write here 10, then here I will write 20, and here I will write 30, and here I will write 40. So you see, in the same length of the mercury, of the thermometer, sorry, you will show less number of readings. The range should be small. I have done this on a paper. Let me show you. I hope you can see that. So here is the original one. So here was 10, 20, 30, 40, 50, 60, 70, 80. So I have 10, 20, 30, 40. So here I have drawn a scale which shows in the same length less number of less range is shown. Okay, so the range of this thermometer is only from 10, 20, 30, 30, 35 something. Okay. So this thermometer is more sensitive. I hope it's a little bit tricky question because it's on sensitivity. I hope that you have understood it. Okay. State one other property apart from volume or expansion which can be used to measure temperature. In thermocouple, we use EMF induced. And in sometimes we also use the resistance of a conductor, and sometimes we use the color of some crystals to show what is the temperature. So they are different. Sometimes we use the pressure of a gas also. So there can be many properties which can be used as a thermonic property and thermometric property. Sorry, I said thermonic. Thermometric property. One of them you have to only write one name. For example, you can say resistance of a conductor. It's a 1 mark question. Resistance of a conductor. I have just mentioned one. You can mention more. There are other properties also. You can mention anyone. Okay, so that's it with the question number 4. Okay, so we are moving to question number 5. Figure 5.1 shows a ray of light that enters a semicircular glass block at A. At B, some of the light is reflected and some light leaves the glass and travels along the surface. State the name of the angle of incidence marked 41 degree. So here, this is the angle of incidence in the denser medium, and you can see angle of refraction in the rare medium is of 90 degree. So this angle of incidence is called critical angle. So critical angle is the answer. It says rays of light are incident at B with different angles of incidence. On figure 5.2a, the angle I1 is less than 41 degrees centigrade. So angle of incidence in the dense medium is less than the critical angle. So if it is less than the critical angle, the light will enter into the air and the light will bend away from the normal. On figure 5.2a, the angle of incidence I1 is less than 41 degree. Draw the path taken by the ray of light after B. And on figure 5.2b, the angle I2 is greater than 41 degree. Draw the path taken by the ray of light after B. In the 5.2b figure, the angle of incidence is more than critical angle. So the process of the total internal reflection will take place here. So the light will not go into the air, it will be reflected. So angle of incidence and angle of reflection will be equal and the light will travel in this way. I have drawn these two figures on a paper. Let me show you them. Figures. So question number 5. So here you see. In figure 5.2 you see the light entered into the air but it bended away from the normal. In the figure 5.2b, the angle of incidence was more than the critical angle. So the process of the total internal reflection took place. So angle of incidence and angle of reflection are equal. So light is reflected, totally internally reflected here. So I hope that you have understood these diagrams. The next question is the speed of light in the glass block is 2 × 8 meter, and the diameter of the glass block is 0.10 meter. The diameter of the glass block is given. Calculate the time taken for the light to travel from A to B. So let's go back to the figure. This is from A to B. This is not diameter. It is the radius. And you know the radius is half the diameter. R is equals to diameter divided by 2. The diameter is given to us. 0.1. The diameter is 0.1 meter. So divide it with 2. You get the radius. So that will be 0.05 meter. From A to B, the distance is equal to the radius of the semicircular glass block. So the distance the light has to travel when it moves from A to B is equal to 0.05 meter. We know the distance the light has to travel, and we also know the speed of the light. So we can find how much time the light will take to travel. So time is equal to distance divided by speed. So just put these values and do the calculation and you will get the answer. Let me show you my work. So time is equals to distance divided by speed. 0.05 meter divided by 2 expo 8, and the final answer will be 2.5 expo minus 10 seconds. So light will take this much time. So that's it with the question number 5. Let's move to the next question. Figure 6.1 is a graph of current against potential difference of a length of metal wire. So it's a IV graph. On the y-axis, the current is represented. On the x-axis, the potential difference is represented. You know, the slope of this graph will be equals to change in current divided by change in voltage. So the slope of this graph is reciprocal of the resistance. Slope of this graph is equals to 1 by R. So whatever will be happening with the slope, the opposite will be happening with the resistance. Remember this. This is a very important point here. The metal wire obeys Ohm's law. State Ohm's law in words. So it's a 2-mark statement. The voltage drop across a conductor is directly proportional to the current flowing through conductor if its physical conditions do not change. So let me show you. I've written this answer. Question number 6 answer is on your screen. Voltage drop across a conductor is directly proportional to the current flowing through conductor if its physical conditions do not change. So it's the equation of the Ohm's law. V is equals to IR. Remember that. V is equals to IR. Okay. The next question is calculate the resistance of the metal wire. The resistance of the metal wire we can find. You can choose any point here, or you can find the slope of this graph. Let's say I take this point. This point is 0, 0. Let's say I take this point. It is 4, 0.2. And let's apply the formula of the slope. Y2 minus Y1 divided by X2 minus X1. You must have learned in your mathematics. So rise divided by run. So it will be 0.2 minus 0 divided by 4 minus 0 equals to 0.2 divided by 4, and so it means the slope is 0.2 divided by 4. But we know that the slope of this graph is equals to 1 by R. So 1 by R is equals to 0.2 divided by 4, cross multiplied, and the value of the R will be 0.20 ohm. Let me show you my work. So I have taken 2 points on that graph. I've noted down their coordinates, and one point is 0, 0. The other point is 4, 0.2. So I have found the slope. 0.2 minus 0 divided by 4 minus 0 equals 0.2 divided by 4, and we know that the slope of this graph is equals to 1 by R. So 1 by R is equals to 0.2 divided by 4, cross multiplied. 4 will be equals to 4 divided. Sorry, R will be equals to 4 divided by 0.2, and the final answer will be 0.20. No, it's not 0.20. Sorry, it's 20 ohm. Sorry, I said 0.20 ohm. It's 20 ohm. This dot is from the back side of the page. It's 20 ohm. I hope that the numerical is clear to you. The answer is 20 ohm. Don't forget it. He says on the figure 6.1, draw a line to show how current varies with potential difference for the new wire. Okay. Sorry. I moved too much. I was here on the B part. Its answer is 20 ohm. By mistake, I moved to the next part. C part is on your question. on your paper, on your screen, sorry. A new wire is made from the same metal as the original wire. The two wires have the same length. The cross-sectional area of the new wire is half that of the original wire. Calculate the resistance of the new wire. You know, the resistance of a wire is inversely proportional to the cross-sectional area and directly proportional to the length of the wire. So there are two wires, the old wire and the new wire. The old wire has a resistance of 20 ohm. It has a certain length. The new wire has the same length. But the cross-sectional area of the new wire is half the original wire. So if the cross-sectional area is half, its resistance will become double, because resistance is inversely proportional to the cross-sectional area. So if you half the cross-sectional area, the resistance will become double. If you make the cross-sectional area one third, the resistance will become 3 times. So here the resistance of the new wire will be 2 times than the resistance of the original wire. So it will be 2 into 20, 40 ohm. I have shown it mathematically also. So 1 mark question. You can use this explanation, but I have done this in another way also. Let me show you. So here on your screen, see first part. R1 is equal to rho L by A, which is 20 ohm resistance. And we know that R is directly proportional to, inversely proportional to area. So R2 will be rho L is the same, density is also the same. Not density. This rho is for the resistivity. But this cross-sectional area is half the cross-sectional area of the original wire. So that 2 will come on the side. Rho L by A, its value is 20. So 20 multiplied to the 40 ohm. So this is I have done with mathematically. But you can also give the direct answer. And because we know that area and cross-sectional area and the resistance are inversely proportional. So if you make the cross-sectional area half, the resistance will become double. Mathematically, you can show it like this. I hope that you have understood. It's a little tricky. It has become a little tricky. On the figure 6.1, draw a line to show how current varies with the potential difference for the new wire. You know, the new wire has larger resistance. Its resistance is double the resistance of the original wire. I've done this on a paper. Let me show you. So I hope that this is visible to you. This is the original wire graph. The new wire has double the resistance. So its slope will be half, because slope here is reciprocal of the resistance. So I use this point at 4. In the original wire, the value was 0.2. So at 4 in the new wire, the reading must be 0.1. So I joined this point with this. So I got this. So you see this new wire has less steeper IV graph, because its slope is less, because its resistance is higher. The slope is exactly half the slope of the original wire. I hope that is clear to you. So that's it with the question number 6. Question number 7 is on your screen. A student connects a thermistor in series with a power supply and a fixed resistor. In space below, draw the circuit diagram of the apparatus. Okay. So here we go. Here I have a battery. I connected it with a thermistor. This is the symbol for thermistor, and this is the symbol for a fixed resistor. So this was what he was asking you to draw. I hope you have understood. Values for potential difference and currents are given in figure 7.1. Potential difference across the thermistor is 8 volt. Potential difference across the fixed resistor is 4 volt. What will be the EMF of the power? You know, the circuit we have drawn. There was only two things. There were only two resistors. One is thermistor and one is the fixed resistor. So the potential drop across the thermistor is 8 and potential drop across the thermistor is 4. So it means that the voltage of the battery will be equals to V1 plus V2. 8 plus 4, 12 volt. It means the battery has provided, the power supply has provided how much voltage? 12 volt. So here you will write 12 volt. The current in the thermistor is 0.018 amp. So current in the fixed resistor will be how much? Because they are connected in series. So there is a single loop. There is a single path for the current. So the amount of current which flowed through the thermistor, the same amount of current will flow through the fixed resistor. So here I will write 0.018 amp. The maximum power rating of the thermistor is 150 milliwatts. In the blank spaces in figure 7.1, insert the values of the electromotive force of the power supply and the current in the fixed resistor. Here and here you have to put the values. A 2-mark question. Then he says, calculate the power produced in the thermistor. If I know the voltage drop across the thermistor and I know the current flowing through the thermistor, I can calculate the power. Power is equals to IV. And it's a 2-mark question. Let me show you my calculation. Here we go. So you can see here, you can see question number 7. I have completed that table. These are the values you have to insert. Power is equal to IV. Put the values of the voltage across the thermistor and the current through the thermistor. Just multiply them, and the answer will be 0.144 watt, which is 144 milliwatt. The power rating of the thermistor was 150 milliwatt. So here we have provided 144 milliwatt. The EMF of the power supply is doubled. Describe what happens to the thermistor. If you will double the EMF, the power dissipation around the thermistor was already 144 milliwatt, and the power rating of the thermistor was only 150 milliwatts. So when you will double the EMF of the power supply, the power around the thermistor will also hopefully double, and it will cross the limit, the rating of the power rating of the thermistor. So what will happen that the thermistor will become very hot. It may blow. It will overheat. Let me show you my answer. Power exceeds power rating of the thermistor. So thermistor will overheat and might blow, or it will melt or blow. So that was the question number 7. I hope you have understood it. We are moving to next question, question number 8. Figure 8.1 shows a simple transformer. So here we have a core which is normally made of soft iron, and here we have a primary coil which is connected to the alternating current supply. Here we have the secondary coil, and EMF is induced in it, and it is connected with a lamp. State the metal used for the core of the transformer. The core of the transformer, which is this core is the core of transformer. This is made of iron, soft iron. Explain how an alternating current in the primary coil causes the lamp to lit. So in the primary coil, you have connected it with the alternating current. You know, alternating current, its direction and its magnitude is continuously changing. So because its direction and the magnitude is changing, so the electric field produced on this primary coil has a changing magnitude and its direction is also changing. The magnetic lines of this electromagnet through this iron core are passing through this secondary coil. And this magnetic field lines, they are changing in magnitude and they are changing in direction also. Due to the change in the magnetic flux passing through the secondary coil, and EMF is induced in the secondary coil. And due to this, what happens? The lamp lights up. It's a 3-mark question, big question, but it's a very famous concept. I've written this answer. Let me read that answer also. Okay. Due to alternating current in primary coil, the direction and magnitude of magnetic flux induced in the primary coil is changing. This magnetic flux through iron core passes through secondary coil. Due to changing magnetic flux, EMF is induced in the secondary coil, which lit the lamp. I hope you have understood. It's a very, very famous question. Transformers are used to produce high voltages for the transmission of electric power over long distances. State one advantage of high voltage transmission. You know, whenever on the power station the electricity is produced and then we want to transmit to the towns and to the consumer, we put their transformers, step up transformers, and we increase the voltage. And why we increase the voltage? Because with the help of the transformer, when you increase the voltage, the current reduces. The amount of current reduces in the transmission line. And you know, the heat which is produced in the transmission line, that is given by I square RT, or the power which is dissipated in the transmission line, its formula is I square R. So by reducing the current, what happens? That power loss is reduced, or by reducing the current, we are able to reduce the energy loss. So by increasing the voltage, actually we reduce the current, and this reduces the power loss in the transmission lines. I've written this answer also. Let me read that. At high voltage, current is decreased. This helps to reduce power loss in the transmission lines. Whenever you increase the voltage with the help of the transformer, by a step-up transformer, the amount of current in the secondary coil is always less than the primary coil. So voltage goes up and the current goes down, and we know the formula of the power loss is equals to I square R. So if the I value will go down, the power loss value will also go down. So this is done. We increase the voltage to reduce the power loss in the transmission lines. So we are done with question number 8. After this, the section B starts. And you know, in today's video, we have only done section A. Section B of this paper, we will do in another video. So, dear students, today we have done, you can see that we have done May, June 2013 paper. Number of the paper is 2-1. And today we have done only section A of this paper. Section B of this paper, we will do in another video. I hope that these videos are helpful to you. Keep working hard. Your answering skills will improve. Thank you very much. Have a good day. God